Hey everybody, welcome to class. Today I'm going to get started. So yesterday you saw this idea of a matrix, which I defined as just this rectangle that has numbers in it. And then I even showed that there were some of these row operations that you were like legally, permitted to do. But now I want to back up. And a lot of books, in fact, there's entire courses uh, about this type of math, and they don't start with solving systems of equations by doing row operations on augmented matrices. That's actually a very advanced thing that we're allowed to do because of the math behind these matrices. But it's a good thing to start with anyway, even though, like I said, some college textbooks don't do that until like 150 pages into the book. It's something that we're familiar with, at least, systems of equations. But now we have to go back further. So we've seen already that a matrix is defined by the number of rows and columns. So this is a, this is a 2 by 3 matrix, 2 rows and 3 columns, and it is not a 3 by 2 matrix. Now, matrices, kind of like numbers, they can be equal to each other, but the only way matrices themselves are equal to each other is if, first of all, they have the same dimension. So in this case, they're both 2 by 2 matrices, and that every element is equal to its corresponding element in the other matrix. So here, these are kind of like weird questions, but they do at least make sure that you understand what's meant by equal matrices. So take a look. What's W, X, Y, and Z in this top question where it says find the value of X, Y, W, and Z? You could type it in to the chat if you want. And in this one, it's being told to you that the two matrices are equal. And then it's saying, if they are equal, what conclusion can you make about X, Y, and Z? And yes, I see from Melissa, X must be 3, Y must be 6, Z must, actually Z, that's backwards. Z has to be the 5, and W has to be 7. That's right. So another thing you can do is here, it's like a little more complicated in the second one. I have 2 equal matrices, and based on this, they wanted to know what the value of X and Y are. And you can set up, it doesn't really become a system of equations because the 5 is the Y minus 3. So 5 equals Y minus 3 and Y equals 8. And the X is equal to 2X plus 2. So a little sort of algebra comes up there. X equals -2. So that's what's meant by equal matrices. Each element in them has to be equal to its corresponding partner. Now, matrices, kind of like numbers, it's possible to add 2 matrices together. And good news for you, adding the 2 matrices is exactly like you would hope it would be. You add the corresponding elements. 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. So you add the corresponding elements, and you get the new matrix, the sum of the two matrices. Well, what do you do if the matrices are not the same dimension? Well, when that happens, this one's 2 by 2, and this one's 2 by 3. So they can't actually be added together. So you can only add together matrices that have the same dimensions. And if you, even on your calculator, try to add two matrices that have different dimensions, it will say error. Here's an example of a matrix equation. This lets us put together the idea of equal matrices and also the idea of adding matrices. Oh, and I see there's somebody wanting to get in off the guest list, and they are now in. Okay, would you take a minute to see what do you think the answers are for X, Y, Z, and W now? Take a minute on that. Okay, and I see from a few people 1, 4, 7, 6, and that is correct because these two things, if you wanted to do like a middle step, the middle step would be something like this. If we, if we wanted to show the middle step, it would be like this: X plus 5, Z plus 2. W plus 3, and Y plus 8 equals. These things are both 2 by 2 matrices. Even though this element has an X and a plus and a 5, that's still like almost like in like a spreadsheet. That's the thing that's like in that like cell. The elements of the matrix, sometimes if you call the matrix, like matrix A is 6, 10, 8, 12, you could call the individual elements, you could say A, like a little 1, comma 1, that means row 1, column 1 equals 6, A, 1, comma 2, that's row 1, column 2. You could identify the different elements of the matrix. But just to mention, this is 2 by 2, even though you could have a complicated expression as the element in the matrix. Now subtraction, again, good news. Subtraction is just like you would figure. You can only subtract two matrices that have the same dimensions. And if they do have the same dimensions, you subtract the corresponding elements, 2 minus 7, 3 minus 6, and 4 minus 8. So far, addition and subtraction are just like we would hope they would be. Now, multiplying, or there's this couple of types of multiplication with matrices. Scalar multiplication is when you multiply like a number by a matrix. Now 5 times 5, 1, 2, 3, 7, 1 is kind of like 5, 1, 2, 3, 7, negative 1 plus another 5, 1, 2, 3, 7, negative 1 plus another, and there would be 5 of them all together. So what do you think happens when you multiply a scalar by a matrix? You could type in what would like the numbers be. You could put on 2 lines in a comment, I guess. And that's right. We do almost like a distributive property thing, where every number gets multiplied by the scalar like that. So far, matrix arithmetic seems like it's a really easy thing. And that's, but here's where that changes. And so the first, 10 minutes of this lesson, 15 minutes, everything is really smooth sailing. But the rest of this lesson is about how to multiply two matrices by each other. First of all, the bad news. It is not what we would hope. It's just, it doesn't equal that. Well, so what does it equal? Well, let me bring up the graphing calculator. Hold on a second. Where is that graphing calculator? I mean, I see it on the screen. I just don't see it on my, let's see. Oh, it is there. Okay, great. So let me clear this out. And I'm going to put in these two matrices. I find the easiest way is alpha, and up here, alpha zoom. And I want to make a 2 by 2 matrix. And I want the numbers to be use arrows, 2, 5, 3, 7. And I'm going to store that into matrix A, second is inverse key, number 1. And I'll do the same thing here, but I'll do alpha zoom, 2 by 2. And this one is 4135. And I'll store that into B. Not that. Store that into second matrix 2. And when I do A times B, second matrix A times second matrix B, I do not get 8, 5, 9, 35, but I get unusually large numbers, 22, 27, 33, 38. So that's mysterious. And to make things even more puzzling, if instead I did B times A, everyone knows that multiplication is commutative, but not in this case. So that's mysterious. How do you multiply two matrices together? Well, I'm gonna tell you about that now. And I'm trying to decide how much detail to give you for this lesson, but let me just think about it as it's going along. Go back to this, to the iPad. There it is. I think what I'll do is first I'll show you how to do the multiplication. And then I'll explain to you at the end where it comes from, because we want to know what it is, and we want to know why it works. But I think by first showing you what it is, it will be easier to understand why it works, or if you get confused by why it works, you might not know how to do it. So let me teach you how that happens. So the question was 2537 times 4135. The way this works is, first of all, these matrices happen to be the same dimension, but I should let you know that if I were to come over here, back to the graphing calculator, and I take like a 2x3 matrix, alpha, zoom, here's a 2x3 matrix. Just throw some numbers in there, 3, 4, 5, 6, 7, 8. And I multiply that by another 2x3 matrix. One, 2, 5, 6, 4, 2. Check out what happens in this case. Error, dim, mismatch. So that's strange because with adding, if two things have the same dimensions, you can only add them if they have the same dimensions. We've seen I multiplied two matrices that were both 2x2 and that worked, but this one gave dim mismatch. And if I come over here and instead I let me go again with this, alpha, zoom, I'll make the 2x3 with some random numbers in there, 1, 2, 3, 6, 7, 2. And I multiply that by something that has different dimensions, but ones that I'm going to pick. Second zoom, let's make it 3x2. 2, 3, 4, 1, 6, 8, 3. Don't need that 3 there. So here are things that I would not be allowed to add, yet that one doesn't give an error. It multiplies and gets large numbers. So I'm going to show you how and when you can multiply matrices together. And then I'm going to justify this sort of strange process at the end after I teach you what the method is. Okay, so here comes the iPad back. Okay, so this is the big thing for today, how to multiply two matrices. Oh, there was someone in the waiting room, and now they are in. Okay. Here you go, everybody, the big thing for the day. First of all, can we even multiply these? Well, what we do is we write down the dimensions. And this first one is a 2x2, and the second one is also 2x2. If these two numbers, whoops, that was supposed to be highlighted. If those two numbers match, which they do, then yes, they can be multiplied together. But if those two things don't match, then they can't be multiplied together. That's why it was not possible to take a 2x3 That's why it was not possible to take a 2x3, or I'll write the word by, times another 2x3, because these two numbers did not match up. So in this case, those two numbers do match up. So yes, it's going to be possible. But what are the dimensions of the answer? Well, that's where the other two numbers come in. These two numbers become the dimensions of the product. So in this case, it's 2x2. And I like to create a little template there. Since I know the answer is going to be 2x2, there's going to be these four slots that have to get filled in. So the number of columns in the matrix on the left has to be equal to the number of rows in the matrix on the right. And the dimension of the answer is going to be whatever these two numbers are, with the rows as the first number and the columns as the second number. So now, what are the mysterious four numbers? Well, here's how it works. To get the number that's in row 1, column 1 of the solution, we take I'm going to, for the purpose of explaining, I'm going to draw a little circle here or an oval. I take the numbers from row 1, and I'm going to combine them somehow with the numbers in column 1 of the thing on the right. And here's how I'm going to do it. I'm going to take the 2 times the 4. So, and you're not able, I sort of put my finger here on the 2, and I put my other finger on this 4. And I think, okay, 2 times 4 is 8. Then I move this finger to the right, so it's over the 5, and this finger down, so it's over the 3. So what I do again, I do 2 times 4, and then the 2, my finger moves over from the 2 to the 5, and this finger moves from the 4 down to the 3. I multiply 5 times 3. I'll write this down. So the calculation I did was 2 times 4 plus 5 times 3 times, which is 8 plus 15, which is 23. So I start at the left of the row and at the top of the column, and I move to the right with the row and down with the column so that the numbers get, and that's why the number of columns has to equal the number of rows, because that's how many numbers there are that get multiplied together. Now, I'm going to start over to do the, and you could actually do these in any order you want. So in order to do the first row, second column, I take the first row of the thing on the left and the second, this is first row, second column, and the second column of the thing on the right, and I do 2 times 1, which is 2, and 5 times 5, which is 25, and I add those together to get 27. Now to get the elements in the second row, first column, I'm going to take the second row of the thing on the left and the first column of the thing on the right. Now I'm going to multiply those together. 3 times 4 is 12. 7 times 3 is 21. 12 plus 21 is 33. And then finally, in this one, to get the second row, second column, I take the second row of the thing on the left and the second column of the thing on the right. And I do 3 times 1 is 3. 7 times 5 is 35. 3 plus 35 is 38. And you will see that that does match up with what the calculator says, 23, 27, 33, 38. Okay, would you take a minute now to go ahead and reverse the order of these two matrices and just see if you're able to get the 4 numbers in the product when I switch the order around. And yes, the number of columns of the thing on the left should equal the number of rows of the thing on the right. Someone want to type in what they get for the 4 numbers in this one? Okay, I see 11, 27, 21, 50, which is correct. And you could pick any of the random elements that you want. There's no special order you have to do it. And if you wanted to start with row 1, column 2, you would just take row 1 and combine it with the numbers from column 2. 4 times 5 is 20. 1 times 7 is 7. 20 plus 7 is 27. And that is how you multiply matrices together. This is like just a little question I made up about when you can multiply matrices together. So here, A is a 2 by 3 matrix, and A times B is 2 by 4. What can you conclude about what the dimensions of B had to be? What are the dimensions of B in this case? Take a second to think about that question.
What do you help find out? Oh, straight, okay. Let's go. Okay, I can go right now.
Okay, so yes, the answer is 3 by 4, because if we had a 2 by 4 solution, something's wrong with my iPad. If I have a 2 by 4 solution and the A was 2 by 3, well, that's good because the first number becomes the rows, but the other one would have to be 3 by, because these things would have to match, and the 4 would have to go here so that the answer was like that. So I like that little question. Here I have sort of a strange thing going on. Here I've got, if a matrix only has one row, it's sometimes called a row matrix, if it only has one row. And if a matrix has only one column, it's called a column matrix. What happens if you multiply a row matrix, in this case, a 1 by 2, by a column matrix, which is 2 by 1? Type out into the comments. What ends up happening? Are you even allowed to multiply these together?
I asked you what the password.
Okay, well, let's start with, can these even be multiplied together? And if so, what are the dimensions going to be of the solution? That's right. It ends up becoming a 1 by 1. So this is 2 by 1. Sorry, 1 by 2. Sorry about that. And this is 2 by 1. So it's going to be 1 by 1. And it becomes 5 times 3 plus 4 times 2, which is 15 plus 8, which is 23. Now, it is not just the number 23, though. It is the 1 by 1 matrix 23. Have you ever seen anything like this before, though? This should remind you of something that you've seen this year. You ever seen something like this? Where you multiply two things together that are kind of like this, and you end up, remember, we ended up with 5 times 3 plus 2 times 4 to get the 23. Have you ever seen that before? When you say it is related to vectors, specifically what about vectors? That's right. This is what happens in dot product. When you did dot product of vectors, you did 5 times 3 plus 2 times 4 equals 23. That one was just a number, not a vector, but see how similar that is? Because matrices and vectors are very much related to each other. Okay, and then I think I'm going to skip these questions for now. This is just more practice with, actually, since 2 of these are not possible anyway, of the 4, why don't you pick which 2 are impossible? Is it AB, BA, AC, CA? Cross off 2 of them for being impossible, and then just calculate out one of the other 2 that are possible. So take a minute on that. In fact, I'm going to put you guys into Zoom groups for a minute on this. Hold on, let me pause the recording. Okay, everybody, welcome back. So you can see on the screen now that A, B, and BA were not possible. AC was this big one, 58, 64, 139, 154, but CA was even more numbers. It ended up becoming a 3 by 3 matrix with all those numbers in it. Oh, someone had an issue, got kicked out. I'm not sure what happened because I'm kind of new to the Zoom with the breakout rooms. I might have not, I might have clicked something wrong. Let me know if that happens next time. Okay, so the final thing for today, and there's only, there's about 15 minutes left. And I want to tell you about this really weird, like, why do we multiply matrices that way? Well, one like kind of unsatisfying explanation is this. You don't have to write this down, I just want to show you. Imagine there was a track meet and there was 9 events. And if your team wins first place in an event, you get 5 points. Second place, you get 3 points. Third place, you get 1 point. And I wanted to figure out how many points did each team earn. So to figure out how many points team A got, I would do, they got 6 first place, so I'd do 6 times 5, and then add it to their 2 second places, which is 2 times 3. And then add it to 1 times 1. And I would do that for all 3 of these. Well, that kind of looks like what you do in matrix multiplication. So check this out. What I've done here, oops, on the bottom, I modeled this as I took the teams, team A, B, and C, and I put their number of first place, second place, and third place finishes into the first row of the matrix. And for B, their first place, they had 4, 5, and 0, and C had 7, 0, and 2. And then I multiplied by the 5, 3, 1. And in doing so, I end up with these 3 answers, 6, 2, 1, and 5, 3, 1, I'd end up doing exactly that multiplication. 6 times 5, 2 times 3, 1 times 1 gets me the 37. On the other hand, to take team B, when I multiply the 4, 5, and 0 by the 5, 3, 1, I get their total points. So this is like a real life like application where we end up doing the same sort of operations that you would do for matrix multiplication,